Greetings. In this video, I'll be talking about homomorphism of a group, so group homomorphism. And the point here is that homomorphism can take place between all sorts of algebraic structures, including other algebraic structures and groups. But in this one, we're concentrating on group homomorphism. So the point here is that homomorphism in general, it's a function, in general denoted as f. For example, a function, and this function f is a homomorphism from G to H, where G and H are two arbitrary groups that I'm talking about. And yeah, so the pronunciation of this entire thing is f is the homomorphism from G to H. Now, G and H are two groups, and let's say G will have operation star and H will have operation. So G is the group from which it goes, and H to which it goes. H will have another operation denoted differently, a circle namely. Very common ways of denoting operations, and showing that these operations are not the same necessarily. So here the point comes that basically homomorphism can be summed up in this following way. For any two elements A, B inside G, this equation applies, and that is as following. This function f, which is the homomorphism from G to H, of the argument A star with B equals f of A in the other group's operation with f of b. Alright, so solely the function with the argument being these two elements from G under the operation of G itself, of the first, namely the first group, equals to f of A and f of b, so these two elements inside the function f, from these two elements from G inside the function f, in operation of the second group together. So basically, f of elements a, b from G under G's operation equal to f of A and f of b also being in another binary operation, but using this operation of circle which belongs to the group to which it goes. Alright. So this is this equation that basically describes homomorphism. And now I can give an example for this. So a concrete example, probably the simplest example to take, is the idea of the properties of exponents, by which it's a very nice example to show. So let's say we have homomorphism alpha, so function alpha is homomorphism from group of integers with under addition, alright, to the group of reals, non-zero reals to avoid problems, under multiplication. Now, how to verify this? Well, it will depend what the alpha of x is. So this alpha is homomorphism from this to this, but also I will define alpha of x as an actual function. I will say some real number to the x, and we will verify that indeed this will work out, that this equation will work out. Why it will work out is thanks to the properties of exponents in this case. So the point here is that first of all we should also verify if these two things actually are groups. So integers under addition, well, they have an identity which is 0. Inside integers, they have inverse, which is always the minus number to whatever is concerned. Any element just multiplied by -1 will be the additive inverse element to an element inside the integers group, and so on. Then here we can verify for identity and inverse. Well, identity will be 1 for multiplication on real numbers, and its non-zero inverse will be always 1 over the number, but thanks to it having not the 0, the problem of 1 over 0 is avoided. So both these things are groups, and now we can verify this idea to see, is alpha, the function alpha, a homomorphism from integers under addition to reals, non-zero reals under multiplication. So let's verify this. Well, f of a star b, what will namely be here is 5 to the a star b, because basically f of x is now 5 to the x. That's the alpha of x, right? Because now we're not doing f in general terms, now we're doing this concrete alpha. And this concrete alpha of x is equal to 5 to the x. Then this should be equal to f of a times or in operation of the second group with f of b. And f of a and f of b is 5 to the a and 5 to the b, namely with this alpha of x. Now, the operation between these two terms won't be star, but it will be circle, because the star belongs to the first group and circle belongs to the second group. Alright, so what will it be actually in concrete terms? Well, the star in this case, in the first group from which it goes, is plus. So what we're verifying is if 5 to the a plus b equals 2, and now here on the right side, the circle is the h, the group to which the homomorphism is. So in this case, it's multiplication. So we're verifying is 5 to the a plus b equal to 5 to the a times 5 to the b, and indeed, thanks to properties of logarithm, it can be verified that it is, because these things will add up with the same base. And so this can be verified as homomorphism. So alpha from integers under addition to non-zero reals under multiplication is homomorphism group, homomorphism from this group to this group. That's an example of it. Alright, so in general, just to recap all of this, basically group homomorphism, what it is its function from one group to another, in such ways that from the first group we take two terms, and this function evaluated at the first group's operation, binary operation of these two terms equals to the function valued at the first element and at the second element, so two elements from G, first element and second element, and between them is the operation of the second group, the one towards which this arrow points inside the homomorphism notation.